And that's it. Alrighty, so here's your video for today. I wanted to go back a little bit in time and just review our titration setup and what we're doing here, because I'm seeing some confusion on some of the titration questions. So when we see a question that says such and such was titrated with, the thing that is titrated, that is your analyte, okay? So the analyte is the thing being titrated. Okay, so when you hear that language, right, the analyte is the thing being titrated, the titrant is the thing doing the titration. And remember, the titrant is the one that we know stuff about. It's the one that we know the concentration and we've measured the volume that we've added. That is where we're starting with. We are using the titrant to find out about the analyte. Usually this means we are using the base to find out about the acid. So in our calculations, we are starting with the information about that base. Okay. So here we did a quick sample question. Looking at some data. This was just quick and dirty from, just playing from the lab. But we see we can use our data to find the volume of the base that was added. Then to figure out moles of HCl, again, we start with our sodium hydroxide, the volume of sodium hydroxide added, get it into liters. Then we can use our concentration in order to get to moles of sodium hydroxide. Then we use our mole ratio to get from moles of sodium hydroxide to moles of HCl. Then if we want to get all the way to concentration of that HCl, we want to go ahead and divide by the volume. And that's that original volume of the sample of the acid that we were testing. Okay. Let's see, then in class we did this warm up today where this is like a word problem for titration, right? And again, first step is analyze that problem. We're going to work on this a lot next class, but look at the problem. What information goes with what substance, what question is actually being asked, and then make sure you have a balanced chemical equation. From this point forward, you must have a balanced chemical equation to work with. Anytime we're trying to talk about how much can we make, how much do we need to use, what amounts reacted with what, we've got to be using mole ratios, which means we've got to have a balanced chemical equation. All right. But again, notice that we're starting with the base, right? We start with our volume of base, we get to liters, we use our concentration, now we have moles of our base, then we use our mole ratio. This one happens to have a 2-to-1 mole ratio for the acid to base, so we plug that in, divide by the volume, and you get your concentration. Alrighty, so then we just looked at our data and saw, hey, titration works pretty well, right? All the data for the different unknowns is pretty much in line, and that's pretty good confirmation that this technique works quite well. You guys did a really good job in the lab. All right, so then in class we talked about limiting excess and excess reagents, theoretical, and percent yield. So again, we just defined limiting and excess reagent. Limiting reagent is the one that you are limited by, the one that will eventually determine how much product can you make, right? You can think back conceptually to our stoichiometry lab with our acid and carbonate to kind of remember those ideas. Excess reagent is the one that there is extra. There is some left over in the end. To determine limiting reagent, right, I recommend that you just figure out how much you could make, right? Answer the question, then pick the one that makes less. That's the way you're going to know for sure which one was limiting, and bonus, now you have the answer, okay? So here was the really simple example I gave you. I'll look through the rest of our notes, and then I have a much more expansive example to do with you right now. So then again, just definitions. Theoretical yield is how much you can theoretically make. That's all we've been doing so far, really, is that the math. If I start with this much stuff, how much product can I make just based on stoichiometry? Your actual yield is if you were to go into the lab and actually do the lab, how much do you actually make, right? It's your reality, your real number. And then percent yield is just a comparison of those two. It's a way of checking how good did you do on the lab. Alrighty, so that's your percent yield. So let's look at an example that really pulls on all of this stuff. Alrighty, so here we go. You have 150 milliliters of a 2.5 molar solution of iron 3 oxide, and it is reacted with 8.35 grams of aluminum metal. Let's just focus on part A. Determine the theoretical yield of iron metal. Okay, so I'm looking at this and I need a balanced equation. Number one, first thing out the gate, I must have a balanced equation. So I'm going to do that first. Iron 3 oxide. I know that's an iron 3 plus. I know O is a 2 minus. So my formula there must be Fe2O3. And I'm going to react that with, let's see, that's aqueous. I'm going to react that with my aluminum metal. So here's my aluminum. Now I can see that this must just be a single replacement reaction, so I can predict my products. And my products are going to be, let's see, is aluminum more reactive? I'm going to check my solubility rules. It is, so aluminum can take the place of iron. So I'm going to end up with Al2O3. Aluminum is also a 3+ ion. Again, that will be aqueous. And I'm going to make iron metal, right? Great. Okay, so there's my balanced chemical equation. Notice the question never asked me to write a balanced equation. It never asked me to translate iron oxide into a formula. It never asked me to predict products or identify my type of reaction. I just have to be able to do it. Like I said, that work is now background to the work that we're trying to do. So now that we have our chemical equation, let's balance it. I think I need a 2 here, and I think I need a 2 here, and then I think we're all done. Okay, so now I have a balanced chemical equation. Now I can move forward. So like I said, when determining theoretical yield, we have to look at limiting and excess reactant. Well, limiting is more important. So I'm just asking for theoretical yield. You need to know, and you don't yet, we just started learning this, right? I'm just showing you an example. You need to know that in order to determine theoretical yield, you have to know which is your limiting reactant. So we are going to do my approach, and we're just going to solve it starting from both reactants, and then we know that the one that makes less is the winner, basically. So let's see here. We'll start with our 150 milliliters of our iron 3 oxide. And I'm going to get that into liters, so I'm going to convert, and I know that there are 1,000 milliliters in every 1 liter. Then I can use my concentration. I know for every 1 liter, I have 2.5 moles, again, of my iron 3 oxide. Okay, now I'm in moles of iron oxide. Great. I'm looking for my product, and the product I'm looking for is iron metal. So I'm going to work towards that so that I am answering my question with all this extra work I'm doing. So now I'm going to go with my mole ratio, and I know that for every 1 mole of Fe2O3, I have 2 moles of iron that I make, and I'm getting this directly from my balanced equation, right? That is my mole ratio. All right, now I'm in moles of iron. Now it just says yield. Normally, we would not report yield in moles. I should have probably said in grams. I'm going to go ahead and take it to grams. When in doubt, assume that you want to go to grams. That's just general advice. But obviously, if I don't specifically ask for it, I can't hold you to it. But grams is a better, because we can't measure number of moles, right? But we can measure grams. You're going to need it later anyways. So now let's go ahead and take it all the way to grams. And we know every 1 mole of iron has a mass of 55.85 grams of iron. And now I'm in grams of iron, so now I'm done. So I'm going to go through and double check. I'm going to cancel my units. My milliliters are going to cancel. My liters will cancel. Moles of iron oxide cancel. And let's see, moles, oh, this is moles of iron. Good. Moles of iron will cancel. And I am left with grams of iron, which is totally what I want. Punch it into my calculator. And I've got my my 150 divided by 1,000 times 2.5 times 2 times 55.85, right? That gets all of my factors in there, and I get an answer with some rounding of 41.89 grams of iron, okay? If iron oxide is my limiting reactant, then that's how much iron I'm going to make. I don't know if it is or not, so now I'm going to go down, and I'm going to try to get a darker green so that I can use a better color. Give me my green. I want it darker. Sorry, I should have done this earlier. There we go, dark green. Good. Perfect. Okay. So let's start with our other reactant, and our other reactant was our aluminum metal. So this time I'm starting with grams. So I have 8.35 grams of aluminum. Now I'm going to go grams to moles. I know that aluminum has a molar mass of 26.98 grams because I found it on my periodic table. That is for every 1 mole of aluminum. Now I'm in moles of aluminum, so now I can do my mole ratio. See, this one's a little quicker. I have fewer conversions on the front end of the problem. So now I look at my reaction, and it is 2 moles of aluminum for every 2 moles of iron. Now I'm in moles of iron. Awesome. But again, take it all the way to grams. You want to be able to compare these things evenly. For every 1 mole of iron, just like from above, we have 55.85 grams. Again, that is iron. we'll go through, we'll double check our numbers or our units here. Grams of aluminum cancel, moles of aluminum cancel, moles of iron cancel, and we are left with grams of iron, which is precisely where we wanted to be. So here we have 8.35 divided by 26.98 times 2 divided by 2 times 55.85 for an answer of 17.28 grams of iron. Clearly, the bottom equation produced less iron, so aluminum must be our limiting reactant. So to finish this off, I would say, okay, boom, right there, that is my theoretical yield. I want to make sure that whoever is looking at this knows that that's the one I'm choosing. That makes aluminum my limiting reactant and iron oxide my excess reactant, right? I can see that I've done the analysis, I've thought about limiting reactant, and I know how much product I should be making. All right, part B. If the reaction actually yields only 15.18 grams, when you do the lab for real, well, then what's that percent yield? Again, let's remember our equation, right? Percent yield from the previous page is simply your grams of actual divided by your grams of theoretical, right? Actual yield over theoretical yield times 100. So let's see, actually I got my 15.18 grams. Theoretically, I should have gotten 17.28 grams. Divide that, multiply by 100, and I see that I got an 87.67% yield. Not too bad. Okay, again, 100% yield, next to impossible. Now, for part C is a whole extra step, and I want you to be able to do this because this now is combining some stuff we worked on last unit, right, of trying to separate out into ions. I'm gonna have to pause it and go to a meeting right now, but I'm gonna come back and finish recording, and then I'll post it a little bit later, which you don't need to know, but there we have it. All right, back in action. So to answer this last question, what is the concentration of iron 3+ ions remaining in solution? This one is going to require some thought, right? We need to do some strategy here. So we need to think about our reaction and what's going on here. We have a certain amount of iron oxide in solution there to react, right? We determined that the iron oxide was our excess reagent. So there is going to be some of that left over. Any of that iron oxide that is left over that didn't react, all of the iron ions in the iron oxide will be in solution, right? We know that when iron oxide is aqueous, that we have iron ions and oxygen ions. So all we need to do is figure out how much iron oxide is remaining in solution. Then we can figure out how many iron ions are remaining in solution, and then we can get the concentration by dividing by the overall volume of our solution. So this is how I would go about it. We need to figure out two things. One, how many moles of iron oxide do we have in the first place? And two, how many moles of it did we use? We haven't figured any of that out yet, so let's do that. So to figure out the moles of iron oxide that we had originally, I am going to just go to moles from our volume and our solution. So we'll start with figuring out the moles of iron oxide we have. All right, that's our first step. So for moles of iron oxide we have, we're going to start with our 150 mils. We'll go to our liters. We know that there are 1,000 milliliters in 1 liter. Now we're in liters. Now we can use our concentration. And our concentration, where was it? Blah, 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 was 2.5 molar. So for every 1 liter, we have 2.5 moles of our iron oxide. That'll get us our original moles. Run the numbers, right? 150 divided by 1,000 times 2.5. And we get 0.375 moles of iron oxide. Now, this is how much we had at the beginning, right? So now let's figure out the moles of iron oxide we used. So moles Fe2O3 used, right? So to do that, I'm going to start with our limiting reactant, and instead of going to our product, I'm going to go to our excess reactant to the iron oxide to figure out how much of that we need to react with all of the aluminum. So I'll start with my aluminum. I know that I have my 8.35 grams of my aluminum. and I'm going to figure out how many moles I have. So that's my molar mass conversion, so 26.98 grams for every 1 mole of aluminum. Now I'm in moles of aluminum. I can use my molar mass, my mole ratio conversion, but this time I'm going to go aluminum to iron oxide. So I know from my balanced equation there are 2 moles of aluminum for every 1 mole of iron oxide. Now I'm in moles of iron oxide. That's all I want to do. So I'll run the numbers and I get 0.155 moles of iron oxide that we used, right? Now, if we just take these 2 things and subtract, we will get the remaining moles. So I'm just going to do that really quick. So 0.375 minus, so 0.375 minus 0.155 equals a number which is 0.22 moles of iron oxide remaining. All right, now I'm gonna just, I don't wanna shift this up. I'm gonna shift this up just a smidge. There we go. All right, so that's how much iron oxide we have remaining. But again, we want concentration of iron ion within that. So we'll start with that. So I'm gonna say, all right, I know that I have, so now we're gonna do our final calculation, moles per liter of iron ion, okay? So we'll start with our 0.22 moles that we have remaining. That's all the work we just did, right? So we know that we have 0.22 moles of iron oxide. So now I want to know, okay, well, how many moles of iron ion is that? I know that for every 1 mole of iron oxide, right, look at the formula, I have 2 moles of iron ion. Okay, now I'm in moles of iron ion. I don't want moles, I want molarity, so I'm just going to divide by my volume. So 1 on top, divide by my total volume, and that's up here at the very top. We know we have 150 milliliters. The other thing we added was a solid, so we're going to stick with that 150 milliliters, although it's molarity, so I want it in liters. So I'm just going to do this one in my head and say that that is 0.150 liters. Now, I look at my stuff and my moles of iron oxide cancel. I'm left with moles of iron ion, and I get an answer of 2.93 molar iron ion. And that gets me my answer to that last question. So this is an example of probably the most complex type of problem that you're going to see, right? It's making you assume the parts that you need to do. It's asking you to go through and do that percent yield. And then this last one asking you to take it even further to look at an individual piece of a formula, really tying in some of the stuff that we did in topic 5. So I would see, especially this last question, as, you know, fodder for midterm, right? This is a great midterm style question where we're really looking at the formula as well as the stoichiometry. But everything else, A and B, for sure, super fair game for Alt6. It's the combination that we could look at with the midterm coming. So I hope this was helpful, and we'll do a lot more practice next class. Please be practicing through those titration problems. We will be having a short quiz next class on everything from Alt6 except limiting and excess. That will not be on the quiz. And then wrap-up day after spring break, and then Alt6 test with the midterm coming right after it. So happy studying.